Zedelef's core technology is an optical transducer that is able to convert an optical signal into an electrical signal. This is one of our products. As you can see, it has 2 pins for the electrical input and 1 optical fiber for the optical output. This version is a ruggedized version that can withstand high pressure and extreme temperatures. We also have another version, which is this one. This is PCB mountable and it has 6 pins. So 2 are for the electrical input, 2 are for measuring temperature inside the device, and 2 are to power a heater that can heat up the liquid crystal if needed. Our technology is based on liquid crystals. So what our device is basically a variable reflectance mirror based on a liquid crystal cell. When you apply voltage, the liquid crystal cell will reflect more or less light depending on the voltage you apply. In this way, we are able to read the voltage by using an optical fiber. And that gives you many advantages, because once the signal is converted from the electrical domain into the optical domain, you can leverage all the advantages that you have with optical networks. And they include multiplexing, long distances, and immunity to electromagnetic interference, for instance. Based on our optical transducer technology, we have developed an optical telemetry system, and we'll show you in a moment how it works with 3 sensors. So we have a gas sensor here, we have a flow meter there, and we'll show also how to read a microphone here. This is the system, and this is how it works. We have a headend box here, which contains a light source. It's a broadband light source that contains many wavelengths, or channels, as we call them in wavelength division multiplexing terminology. All the channels go to the backbone fiber, and at the head-drop filters, some of the channels are branched off, and they are directed to the corresponding sensor. The rest of the channels go through, and then we can daisy chain as many head-drop filters we want. In this case, we daisy chain another head-drop filter, and we branch off to read another sensor here. So once the light of the appropriate wavelength reaches the sensor, the light is reflected back by our optical transducer, and it goes back along the same way through the filters and back to the head-end box. In here, light is divided again into many channels, and each channel is read independently. And the electrical output from each channel, which is directly proportional to the intensity of the light that arrives at the photodetector, is then read through this computer here, which we don't have. In this case, we can see in real time the electrical input at the 3 sensors that we have connected. Let's start with the gas sensor. Here we have retrofitted the standard gas sensor with a 4 to 20 milliampere output. What we did, we connected the 4 to 20 milliampere output to a voltage control oscillator in order to generate a square wave of a well-defined frequency. And then this signal, the square wave, is applied to one of our optical transducers that's inside this box. And the optical signal that we read is then read at this end here, and it's shown in the display. So this is the signal that we read optically from the gas sensor, and this is the corresponding reading once the frequency is converted back into the oxygen percentage. This is a flow meter that we also have retrofitted with our optical transducer. It's an oval gear flow meter that opens and closes a circuit every time the wheel turns. In this case, we convert that open-closed circuit into pulses, and then the electrical pulses are applied to one of our optical transducers that sits inside the case. Then the signal is read optically, and the pulses are counted so that we can retrieve the flow rate. In this case, I can also change the flow rate, and you can see that this is a real-time measurement. So I can change the flow rate to high or low, and we get a real-time reading of the flow rate. Another sensor that we can use is a simple microphone. In this case, our system is completely passive at the sensor end, because the voltage generated by the microphone is directly applied to one of our transducers. So for instance, we can use this system to transmit voice over fiber. Now I'm demonstrating this with an iPhone. We can connect it straight into our optical transducer, play a song. Now, if you can hear the song properly, it means that our response is very linear and at the same time that the bandwidth is quite large in the kilohertz range. So that shows how it's possible to transmit voice over fiber, and this is to prove that it is over the fiber. If you bend it, of course, you don't hear anything.